Welcome to the UQ Centenary Science and Magic Show. May I introduce ourselves? My name is Horst Schirrer. This is Kirsten Laurie, Jakov Kulis, Andrew Stevenson, and Chris Wright. And we're here to take you on an action-packed romp through chemistry and physics, the two science disciplines that are the most fun. Forget mathematics and biology. Okay, let's start the show with a good old-fashioned countdown and a bang. It's counting 10 to 5. There we go. 2, 1. Welcome to the show. Okay, as I said, we're going to take you on an action-packed romp through science. What is science? Science is the biggest human endeavor that has ever existed in human history. It is venturing forth into the unknown and finding out how the world around us works. In order to do that, scientists usually start with a hypothesis, with an idea of how the world works, and then do experiments to see if what they thought really is the case. And then they learn from the results of the experiments. The two keywords in there are testable. If we can't test it with an experiment, it's not science, it's fairy tales or fiction. And the other keyword is experiments. So you're going to see a lot of experiments today. One caveat though, do not try anything of what you see here today at home. We are what you called trained professionals. And that is why we are doing the experiments for you. Now, what is chemistry? What is physics? Physics is the study of matter all around us. So if I look at this lectern and study it very intently, then that is physics. Chemistry is the science of how to transform matter from one state into the other. So as a chemist, I look at that lectern and go, how well would this burn? Be warned though, even though the title of the show it's magic and it's science, there really is no magic around here. All we do, we know how it works and we control the things. We know what is happening and there's really no such thing as magic. Or is there? Suddenly the bottle turned blue. What did I do to that bottle? I shook it. And what happened while I shook it? It turned blue. But why? Because can you see, the bottle is not quite full. There's air above it. And each time I shake it, I put air into the solution. And air contains what? Oxygen. And suddenly the bottle turns blue. What we have here is called a redox reaction in chemical terms. Each time I shake the bottle, the solution in this bottle reacts with the oxygen in the air and it turns blue. And as soon as the oxygen is used up, it turns white again. And then when I shake it, it turns blue again. And if I leave it stand, then eventually it will turn white again. And so on and so on. I can do that over and over and over. And in fact, we set that bottle up about an hour ago. Since then, we've just been keeping on shaking it. So, science, as we know it.
Okay, so I think we can take this a step further here. What Horst has done with that blue bottle is he's produced a chemical change. And in that case, it was a color change. But in order for him to get that color change, we had to shake the bottle. And then in order for it to go colorless again, we had to leave it stand still. So I want to do one better, and I want to do a color change reaction in this beaker here, so that it changes color automatically, and not just once, but multiple times. Okay? So what I have here is I have a beaker with a clear solution on top. This contraption underneath is actually a stirrer. It's going to do nothing to the reaction other than just stir it, so I'm not cheating. So what I'm going to do is I'm going to add another colorless solution into here. And I'll start some stirring. Can anyone see a colour change yet? Okay, I'm going to ask that again with my secret solution, again colourless. And there we go. With our fourth solution there, we actually see a colour change immediately to orange, and then that changes to a darker colour. And as that stirs, that's going to keep oscillating from one colour to another. Now, the reason this is oscillating here is because we have not one reaction going on here, but two. And those two reactions are coupled together. So when one reaction is slow, the other one becomes fast, and vice versa. So these chemical reactions oscillate from one state to another, and hence that's producing the colour change we see. As cool as this is to look at, these sorts of reactions, these oscillating reactions, are actually quite important. You have many of these sorts of reactions occurring in your body all the time. So I'll let that stir there while I give over to Kirsten here.
Okay. So we've seen a few different types of chemical reactions. We've seen some that release heat, like the balloons at the start, some that change colour, like these ones here. So now we're going to keep exploring different types of chemical reactions. There are obviously heaps of different types of chemical reactions that release energy in all sorts of different ways and do all sorts of different things. So, what do you think is going to happen when we add this horrible black solution into these flasks here? All right, let's find out. Can we get the lights off, please? All right, so can someone tell me how this reaction's releasing energy? Light? Did someone say light? Yes, that's right. So more specifically, it's releasing energy through a process called chemiluminescence. And can anyone tell me where you might have seen this sort of chemistry in everyday life? Yes, glow sticks. So you can see we can get different colours based on what colour dye we have in there. Thank you.
Okay, so let's change the topic a bit here. We've seen some chemical reactions that change colour so far. Let's look at some chemical reactions that change volume after they react. So this demonstration I'm going to do for you here today actually involves something many of you may have used at home. So how many of you have actually used hydrogen peroxide at home to clean up a cut or a scrape? Yep, some people here. Good, good. So hydrogen peroxide is basically composed of water and oxygen. Now, the stuff that you guys buy at the shops to clean up your cuts is quite less concentrated, okay? It's safe to touch and it only kills bacteria. The stuff we're using here today is 10 times as concentrated, so it will not only kill bacteria, but it will seriously injure us if we touch it. So, on that note here, we have two measuring cylinders. What we're doing here is we're adding some detergent into the bottom there, and we're adding some food colouring there down the sides. As well as what we have in there is we have some hydrogen peroxide, the concentrated stuff. And I'll just point out that this demonstration here is actually called elephant's toothpaste. Now, I'm not going to explain any more on that. I'm going to let you guys decide why we name it that and see if you can figure that out. So in order to get this reaction started, what I need to do is I need to add a bit of a secret ingredient here. Okay? So I'm going to get this reaction started here. And there we have it, ladies and gentlemen, elephant's toothpaste. So without further ado, Horst and Kirsten can start brushing their teeth. Thank you.
All right, so I have a question for you all. We've been talking a lot about chemicals. What's the most, or at least one of the most important chemicals for us as human beings? Oxygen and water are the two most important things. Without them, we are stuffed. Now, we have a device the University of Queensland has been developing for about 5 years now to measure a person's lung capacity. It's called a breathable air gasometer. I've been lucky enough for these centenary celebrations to be able to borrow it and bring it here today. Now, is there a volunteer from the audience who'd like to measure their lung capacity? All right, mate, blue shirt. What's your name? Anthony. Big round of applause for Anthony. Come on down. Now, Anthony, the breathable air gasometer is also known as a bag. Now, simple question, do you think you can fill this bag with air? One breath.
No.
No, I don't think so either, because this is quite a large bag. All right, so what we're going to do is, I just want to double check, no cheating. We're going to make sure there's no air inside the bag. So we're going to squeeze all the air out. Now, if you could hold on to that. Now, first, a couple little tips. 3 main things. 1, when you blow, make sure you actually let go of the bag a bit. Release the pressure in your fist. I kid you not. I saw a high school kid one day blow into his fist as hard as he can and wonder why I wasn't blowing up the bag. A bit scary. Anyway, 2, when you blow, don't feel the need to just pull the bag over your head. Bad idea. And 3, if you start blowing, keep blowing, keep blowing. If you start feeling dizzy or seeing spots, probably a good idea to stop at that point. But until that happens, I say go crazy. All right, so I'll stand over this side. If you just hold on to that, I'll hold the other end of the breathable air gasometer. So, big deep breath. Wait! Nah, just messing with you. Okay, whenever you're ready, just blow 1 big deep breath in. All right, let's see how we're going. Let's put this in this perspective. In order for Anthony to breathe out this much air, he's first got to hold this much air inside him. So when he breathes in, big deep breath, he's got a big empty cavity inside him, this big. Now, that's quite a decent size of his chest. I mean, it's practically the size of his head. I think that's a pretty good effort, don't you? Now, as you can tell, or probably tell by now, I do like to talk a bit. Friends say I'm full of hot air, bit of a windbag. So between the two of us, who do you think would have bigger lungs? Me? Oh yeah, I'm slightly bigger, so perhaps I might be, I don't know, perhaps an extra 2 centimetres on that volume. We have a second breathable air gasometer here, which, Anthony, if you can hold on to your lungs for me. Chris will come out. Get you to come out. So this is another breathable air gasometer, just like the first, except this is yellow and blue and a little bigger. Let's see how we go. Trick is you've got to warm up. You've always got to warm up. So, well, I mean, what's happening? I think we've got 1 of 2 options there. Either I am awesome, or 2, I might have used science to help me cheat. What do you guys think? You think I cheated? No way, I did it the same as Anthony did. I didn't. What did I do differently? That's right. I held the end of the bag. I made Anthony hold it like this and blow straight into it, whereas I held the bag open and slightly away from my mouth. And that's the science I was in. Anthony, big round of applause. You can sit back down. So, what I was taking advantage of there, the piece of physics behind that, is called Bernoulli's principle. And what this states is that a fast-moving stream of air is at a lower pressure than the still air around it. So I blow, create a fast-moving stream of air. That air is at a lower pressure than the air around it. Since it's at a lower pressure, it sucks that air in and takes it with it, so you can move a much greater volume. Firefighters actually take advantage of this. You might have seen, I can give that to you, Chris. You might have seen, mainly on a movie or something, they get these great, firefighters have these great big fans. Now, the reason for that is once a firefighter puts a fire out, the job's not done, because lots of people still die in house fires due to asphyxiation. So there's no oxygen, there's just smoke everywhere, they can't breathe. So it's very important that they clear that smoke away as quickly as possible. Now to do that, they get these great big fans. They don't hold it right up to a door or a window, they hold it back about 1 metre. So that way you turn the fan on, it creates a fast-moving stream of air. That's at a lower pressure than all the air around it, and it can move a much greater volume, and you can clear the smoke very, very quickly. Make sense? Great.